So now starting with the very basic, it's rate is what is rate? Rate is proportional to any change that's happening. So it's proportional to any change that's happening at if you measure it, it's delta change. Like you measure the change with respect to the change in time, and time would be in, I mean, you want to measure it in minutes or seconds. So that is what speed is. Speed is you measure change with respect to time. So in a chemical reactions, like in physics, the speed is distance over time. So the how fast is this distance changing with respect to time. In chemistry, there is no distance. So if you want to see a reaction happening, the way you can figure out whether it's happening at a fast speed or a slow speed is you measure the change. So what change are we talking about? In a chemical reaction, this change could basically be anything that is any observable change, anything that is either observable or measurable. And if you want to calculate it mathematically, then it has to be measurable as well. So that change could be a color change. You can I mean, if there's a color that's changing in the reaction, you can measure that, how fast that is happening. It could be a change in the volume of gas. It could be a change in the mass of a substance. It could be a change in the pH. You can measure the pH and maybe the pH is changing. So anything that is measurable or observable, you measure that change and you measure it with respect to time. So, and if that change happens very quickly, that's a fast reaction. If it's slow, that's a slow reaction. I said then. So I'm going to do a couple of reactions first. Let's say I want to figure out how fast is Mg reacting with HCl and it produces MgCl2 plus H2 gas. So I need a stopwatch. Remember, time is very important. You can't measure speed without time. You have to measure time. So what could you do in this reaction? You can measure how quickly hydrogen gas is forming. That's one thing that you could do. And you can time it. So that's one. And you can also measure how quickly or what else. Mg's, remember there's a beaker and you're putting a piece of Mg in HCl, right? So there's a piece of Mg that's being added to HCl. So anything that's observable, you can measure how quickly, how fast does Mg dissolve. And you can time it. Like if it dissolves very quickly, if it takes very less time, then it's a fast reaction. So how fast Mg dissolves. And you can measure the bubbles of gas that are forming. I mean, maybe you can take pictures every 1 second. You can count how quickly the bubbles of gas are then the quantity is decreasing. So the bubbles of gas that are forming, that could be an indication. Mass would be lost, so you can measure how fast the mass is decreasing. The reason mass is decreasing is because the H2 gas is going to escape. So how fast mass decreases, that could be another. So remember, it could be anything that you measure that is observable or measurable, and you can measure it with respect to time. Now the change that's happening, that could be an increasing change, that could be a decreasing change. Your graph might go up, your graph might go down. So one example is, let's say I make 2 axes and I measure I measure the mass of the beaker. So if I measure the mass of this beaker with respect to time, then the mass of the beaker would decrease. It's going to go, and then at a certain point, it's going to become constant. Remember, the mass is decreasing. Why? Because H2 gas is escaping. So that's one thing you could do. And similarly, if you measure the volume of H2 gas, maybe you put a syringe on top and you try and, so if I make that graph, then that graph, the volume of H2 gas would be 0 initially. And then it's going to go. So it's going to go up with respect to time. So the point is, it doesn't matter whether the change is happening in it's a decreasing change or it's an increasing change. What you are looking for is the change. And the gradient of such a graph is the rate of the reaction. So the gradient of this graph is basically your rate. What does the gradient tell you? It tells you how fast is the mass changing with respect to time. Similarly over here, the gradient gives you an idea of rate. Now, the steeper the graph, the faster the reaction. So higher gradient, larger gradient, more steep. So if it's more steep and you've got a bigger gradient, then that means you have a faster reaction at your hand. So this one is going to be.
See, graph जो flat हो जाता है आगे से, इसका क्या मतलब होता है कि
reaction stops, ठीक है? I mean, if it's zero gradient, that means the reaction has stopped. There is no change happening anymore, ठीक है? Clear है?
लेकिन ये नहीं दिखा रहा होता कि volume of hydrogen being produced constant हो.
So that means nothing is happening now. Because
नहीं मतलब hydrogen produce हो रहा है at constant rate.
it shows that the volume is no longer getting produced. Okay, now it's fixed. If this much volume has been produced, then now it's no longer changing. Like if 20 cm3 is produced, and now no extra gas is being produced. So that means the reaction stopped. Clear if?
Yes.
Okay, that means there's nothing happening anymore. Nothing, no change happening. No H2 gas, no extra H2 gas being produced. वो जितनी produce होगी थी वो अब produce होगी, अब कुछ नहीं हो रहा. ठीक है? So anyway, so we've got so that means steeper means faster reaction. If you got a flat line, that means no reaction. So this indicates. Now reactions are normally the graphs are normally you're going to get these two types of graphs. Those are the only two types. I mean, the change could be anything. It could be any change, but normally you just get these two types of graphs. It's either a decreasing change or it's either an increasing change. And the graphs usually have this kind of shape. They're faster at the beginning and they're slower at the end, and then they stop, the reaction stop, because you run out of reactants. Now, this is just a brief idea how you're going to measure rate. You clear? Is this clear? Sam, is this clear? Nadine? Zohab? Zaib, clear?
Yes, sir.
Now, the next part is what does rate depend on? So rate when we talk about rate, and you've studied this in O-levels as well, rate depends on it usually just depends on collisions, like particles colliding with each other. So you've got a bunch of particles. So here are, let's say they are, and let me just, so I've got a bunch of particles. And I've got another, so I've got another bunch of particles, and they are red in color. So anyways, it's basically particles bumping into each other. So there's particles of X reacting with, so there's X over here and there's Y over here, the particles of X reacting with the particles of Y. And they're going to bump into each other, and the collisions, because there's going to be collisions, what would collisions do? Whenever you have a collision, the old bonds are going to be broken, and therefore new, there's going to be violent collisions, like really violent collisions. That is usually what happens when you have a reaction. And when you've got particles colliding, what happens? Old bonds are broken. And you've got new bonds that are going to be so you'll have new bonds that would be formed. So it's all about collisions. Like if you have a so if you have any reaction, the particles need to bump into each other. Now, I mean, that is one of the reasons why there's a lot of chemistry on planet Earth. Uh, because particles really can't collide with each other. Particles can collide with each other in two states. Either it's liquid state or aqueous state, or because in aqueous and liquid states, the particles are moving around, or in gaseous state. In solid state, particles don't bump into each other. I mean, this particle, if it was in a solid state, it won't jump and bump into this particle over here. So one of the reasons why planet Earth is so, like, there's so much chemistry happening, there's so much I mean, the chemical reactions happening everywhere on planet Earth. That's one of the reasons why we either have oceans, there's a lot of water, there's a lot of liquid water, and the particles are all moving around and they're bumping and colliding with each other. Old bonds are being broken and new bonds are being formed. Or we've got an atmosphere as well, which is we've got gases in the atmosphere, and those particles also. So you don't see a lot of chemistry happening on Mars or on other planets, mainly because the most of the stuff is in solid state. But anyway, so it all depends on collisions. And when particles collide, there are two things you have to think about. One is how violently they collide and how frequently they collide. So one of the thing that you have to comment on is the frequency of the collisions. And the other one is how vigorously do they collide? Like how much force do they collide with each other? So it's not just collisions, it's not just particles colliding, they have to collide with each other with a lot of force. So how effective, so one is effectiveness and the other one is the frequency. Like, are they colliding violently enough so that old bonds are broken and new bonds are formed? So whenever you talk about rate of reaction, you're going to comment on these two things: the frequency of the collisions and the effectiveness of collisions. Now, there are 5 factors which would on which everything depends. Factor number one is on which rate depends, that's temperature. So when you have temperature, you have higher temperature, you've got more kinetic energy. And when you have more, so higher temperature means there's going to be more kinetic energy. So that means there's going to be more kinetic energy. And if there's more kinetic energy, that means there's going to be more effective I mean, particles are going to bump into each other more frequently as well. So there's going to be more frequent and also effective collisions. And effective collisions. Second factor is, this is mostly O-level stuff. So second factor is, what's the second factor? It's pressure. Now remember, for pressure, this only applies to gases, only for gases. So it's only for gases, and pressure mein hota hai ki you got a higher pressure, that means the volume decreases. So volume decreases, and when the volume decreases, particles are closer together. And if particles are closer, that means they're going to have more frequent collisions only, not effective. Just more frequent collisions. Because the particles are not becoming more energetic, they're just more particles which are closer together. So they'll just bump into each other a lot more. So the effectiveness kind of remains the same. So effectiveness remains the same. Number three is concentration. Now, when it comes to concentration, you've got same thing as pressure. Now, concentration is a term that only applies to, so it only applies to solutions or to gases. You can't increase the concentration of a pure liquid. I mean, they all liquids and solids are already tightly packed. So it only applies to solutions or gases. Like if you have pure water, the water molecules are already close together, so you can't make them closer to each other. So it only applies to something that is in gaseous state or in aqueous state. Like if you have particles of random molecules, if they are far apart, that means they are dilute, less concentrated. If they are close together and there are more of them per unit volume, then they will obviously bump into each other a lot more, and you will get more frequent collisions. So more concentrated means you have more particles per unit volume. So you'll have more particles per unit volume and more frequent collisions only, not effective. The fourth one is surface area. So if you have, the fourth is surface area. So I'll just go through this quickly. So when it comes to surface area, you have surface areas, you have higher surface area, that means powdered. So in powder state, the collisions are going to be a lot more. So only more frequent collisions. Higher surface area means smaller pieces, powdered. and you will have more frequent collisions. So more frequent collisions only. And the last one is number 5 is catalyst. What does a catalyst do? A catalyst does not increase the, so a catalyst does not increase the frequency of collisions. It just makes them more effective. Like you still have 100 collisions, but now the collisions are way more successful. So what a catalyst does is it lowers the activation energy. And you get more effective collisions. So that simply means that previously you were having 100 collisions and very few, like 10 collisions were successful in breaking the old bonds and forming new ones. But now you have the same 100 collisions, but now 50 of them are successful. So the reaction speeds up. See, so they lower the activation energy. And we did discuss there were 2 types of catalysts. We're not going to go over that in this, but remember these 2 things, frequency and or effectiveness. So temperature does both. Pressure and concentration and surface area, they just increase the frequency of collisions. Catalyst just increases the effectiveness of the collisions. Is this clear? These 5 points. Clear?
Yes, sir.
Yes.
Now the next thing is we're going to move towards, and we're going to discuss the orders of a reaction. So there's a thing called the order of a reaction. So what's the order of reaction? What does it mean? So I'm gonna just copy these collision things. So there's a reaction that's happening over here. There is X and there is Y, and they're reacting together. Ibrahim, आपका आ रहा है, 1 second.
Sorry.
Is this Zoom or okay? So orders of reaction. So okay, 1 second, sorry. This one. Now you have this. You have X and Y reacting. So let's say there is a reaction, and there is some X which is reacting with some Y. I mean, there's a molecule of X reacting with a molecule of Y, and there's X plus Y, and they're supposed to react together to form, let's say, some other random molecule which is Z. And the reaction is happening. Now, let me first also tell you that we are, out of all these 5 factors, we at the moment are only going to focus on concentration. That's it. So, or when you talk about order of reaction, we are ignoring the effect of all the other factors. I'll just add one effect, which is that if you increase temperature by 10 kelvins, the collisions double. So make sure you remember this separately, that the frequency of collisions, they double. So every 10 Kelvin rise doubles collisions. So if you keep everything else constant. But anyways, our whole focus on this is not surface area. Catalyst we studied somewhere else, TK. We studied it in transition metals. We studied that in electrochemistry as well, homogeneous catalyst. So catalyst is a topic for some other discussion. Pressure, we're not going to focus on pressure at the moment. But remember, for pressure, I can say that pressure and concentration are directly proportional. Like if a gas has more concentration, it's obviously going to have more pressure as well. So concentration and pressure are terms that are linked, but pressure is only applicable for gases. So, I mean, if you think of it as gases, like if I just move this, so gases that are more, like if I remove this now, they're gases, like no longer a solution. So there are a bunch of particles far apart. So that's a, I mean, you can think of it as a dilute gas, and this one is a concentrated gas because the particles are really close together. So pressure and concentration are kind of almost the same. They behave exactly the same way, and they are directly proportional. So for gases, you usually use the term pressure instead of concentration. But at the moment, our focus is going to be on pressure. So coming back to order of reaction, you've got, so what's the order of reaction? That's the whole discussion. Now, the rate of the reaction, does it depend on the concentration of X? Like, and remember, it depends on the concentration of X. I mean, for example, if I double my number of particles and I make them more concentrated, so I've doubled the concentration of X, then the frequency of collisions would also double because there's more particles. There would be a lot more. They would bump into each other a lot more. So the rate of the reaction would speed up. So rate is dependent on the concentration of X, and at the same time, it's also dependent on the concentration of Y as well. That means we can have this relationship. That rate depends on the concentration of X. It also depends on the concentration of Y. So same thing, if I double the concentration of Y, then the number of collisions would double as well. So the rate of the reaction or the speed of the reaction depends on both concentrations. Okay, is this part clear, this one? Yes or no, is this clear?
Yes, sir.
Now, so we have this, we're trying to build this equation, like, and remember, it's only the reactants. Usually it's just the reactants. Rate is dependent on the concentration of the reactants. I mean, so we can state that rate depends not on the products, because the products are not doing anything. Once they are formed, that's it. So rate depends on the concentration of the reactant. So reactants, remember, square brackets is concentration. Now there's one thing I'm going to add to this, and that is I'm going to add a power over here, which is A, and this over here is B. What this means is I know that rate is dependent on the concentration of X, but I don't know exactly how it's dependent. Like if I double the concentration, maybe the reaction rate would double, but maybe it might increase 4 times, or it might increase 8 times, or there's a small possibility that it might not increase as well. So I know that the concentration of X over here will affect the rate of reaction, but I don't exactly know how it's going to affect that. So A and B are known as your orders. They're known as the order of a reactant, of a specific reactant. So the term order means it's simply, and I can get rid of the proportionality sign as well. If I want to get rid of it, there's going to be a constant as well. That's going to be known as the rate constant. We'll talk about that. I mean, because, and this entire thing is known as a rate equation. So coming back to order, what is order? Order is, it's the exponent, or in simple words, it's the power of the concentration of reactant in a rate equation. So that's the proper definition that they're going to ask you. So that is the order of
order?
हाँ
मतलब order की concentration.
नहीं order की definition है कि if they're going to ask you what is meant by order of a reactant, so it's this power over here which is A and B, right? We know that the rate depends on the concentration of X. We just don't know how exactly it depends on the concentration of X. And we know that it depends on the concentration of Y, but not exactly. Like if it's directly proportional, I mean, A could have a value of 1. That means rate is directly proportional to the concentration of X. We'll discuss the values of A in a short while, but is the point clear that this thing is known as a rate equation? That rate depends on the reactant concentration. So rate depends on whatever your reactants are, whether it's X or Y, it would depend on those. And we just don't know exactly how it's going to depend on those. Okay? Which is why we give them powers. At the moment, it's A and B. I mean, A could be 1 and B could be 1 as well. So K is a constant because we need to get rid of the proportionality sign. So that's your rate constant. So is this clear, this thing? Clear,
Yes, sir.
Hamza? Maria, Zoha, is this clear? Nadine?
Yes, sir.
So now we're going to discuss this. And we know what order is. So I'm going to discuss what is meant by these powers. Like, what if the order is 1? And let's say I go back to the proportionality sign, like rate was dependent on the concentration of X. I'm just going to ignore Y for a second, and it had a power of A. So if A is 1, then that means that's a direct proportionality. That's directly proportional. So that is what is meant by order 1. So that is what is meant by order 1, that it is directly proportional. And the graph of such a reaction, is going to look.
क्या मतलब? I didn't get it. I mean, what if it was 2? तभी यही होता. Directly proportional.
No, then it won't be directly proportional. I mean, at the moment, I'm assuming, let's say A has a value of 1, right? So just focus on 1. Okay, let's say it's 1. So if it's 1, that means, I mean, this is direct proportionality. Like you change the concentration of X, the rate would increase proportionally. Like if you double the concentration of X, the rate would also.
Yeah.
So that's a direct proportionality. That means you double the concentration, the rate would also double. So this is directly proportional. I mean, I'm going to write this. If you double concentration of X, then that means the rate doubles as well. Right? Now, the next one. What if it's order 0? What does that mean? That if its order is 0. So the relationship would be like this, that rate depends on the concentration of X and the power is 0. So what do you think? What is the relationship like if the power is 0? What does that mean? Like directly proportional, we understand that you increase. So if it's power 0, if I double the concentration of X, what would happen to the rate?
Nothing.
Nothing would happen because any concentration to the power 0 is basically 1. So it would just remain the same. So nothing would happen. So that means changing concentration of X has no effect. So sometimes this will happen, has no effect on rate. Like no matter what value you put for concentration, it's going to come out to be the same thing. It's going to be like if it's 2 mole per dm cube to the power 0, that's still 1. If you increase it 5 times and you make it 10 mole per dm cube and the power is 0, that's still 1. So the rate would remain unaffected. It would have no effect. So that means sometimes what would happen is you're going to keep changing the concentration of X, but the speed of reaction remains unchanged. Nothing happens to it. We'll talk about it, why that would happen, but at the moment, we just have to understand what is meant by order 0. And similarly, you have order 2 as well. So what is order if order is 2? So if I say that the order with respect to a certain reactant is 2, that means the relationship between rate and the concentration of that particular reactant, it's this. So what do you think? What's the relationship? Like if I double the concentration of X, what would happen to the rate?
Increase by 4 times.
So it would increase by 4 times. That means the rate changes by a bigger margin. When you change the concentration of X, if I triple the concentration of X, the rate increases 9 times. So that means rate is really sensitive to the concentration of X. So that means if you double the concentration of X, rate quadruples. So rate of reaction is going to change by a much bigger margin. So that is order 1, 0, and let me just put them in the. So is this clear? What is meant by order? I mean, that's just the first thing, the basics. Clear?
Yes, sir.
Yes, sir.
So you got order 0, order 1, order 2, and you've got a rate reaction. Sorry, rate equation. So rate would depend on the reactants. The power indicates that we don't know how it's going to depend. So the power is going to tell you exactly how it's. So if the power comes out to be 0, that means the rate is not dependent on that particular reactant. You keep changing that concentration, it's not going to change. If you have a power that is 2, that means rate is really dependent on that particular reactant. You change the concentration of that reactant and the rate increases or decreases by a much bigger margin. And so that is what an order of reaction is. And there's a graph which we're going to talk about. So let's talk about the graph for a 0 order reaction. We'll just have time for that, so we'll quickly do that. For a 0 order reaction, so in a 0 order reaction, the graph is going to be a straight line with respect to time. Just a second. So the concentration of X with respect to time. Remember we just made these graphs. Now what's happening to the rate? I told you that the gradient is the rate. And in this case, it's constant. Like you keep
लेकिन ये origin से start क्यों नहीं होना?
नहीं, start में क्या होता है? You have what happens right at the beginning. There's a lot of X, right? Like when you start a reaction, the concentration of the reactant is very high, right?
जी जी.
And then the reactants get used up, so the concentration of X goes down. Is that clear?
Yes, sir.
So over time, what is happening is X again. So over time, what's happening is that the reactant is getting used up. So the reactant will go to 0 eventually because it's going to get used up. But the speed, I told you that the change if you plot the change that's happening and you with respect to time, the gradient is the rate, but the rate is going to remain constant. Like the rate would remain unaffected. So it's going to start at a particular speed and it will just continue with that speed. Usually reactions slow down. Usually reactions are slower, faster in the beginning, and then they slow down. Like if you burn a match, it burns quickly at the start, and then it slows down, and then it dies eventually. It stops burning. You pour a cup of fizzy drink, and initially the bubbles are like the reaction is really fast, but then eventually the bubbles stop forming and they slow down. But in this case, the rate of the reaction is not going to slow down, because it's not dependent on the reactant concentration. So if the reactant gets used up, it becomes lesser and lesser. Its concentration over time decreases, but the rate remains completely unchanged. Is this clear, this graph?
Yes,
sir.
sir.
Okay, just the relationship. Okay. Normally reactions will not follow. Normally overall reactions are never zero order. Normally reactions, they always slow down because the reactants, they get used up. So the frequency of collisions decreases and the reaction eventually keeps on slowing down. So normally the graph would always follow this kind of graph. Like it would be steeper in the beginning and then it would slowly slow down and then come to a stop. So the overall reaction is usually never zero order. So you're never actually going to see this particular graph for a reaction, but we'll just discuss that, just the relationship first. So we'll discuss the other graphs in the next class now, okay? So is this clear? The first one, or what's order and what's
Yes.
and the graph for zero order.
Yes, sir.
Sanity. Let's continue tomorrow then, okay? Okay, everyone.
All right, sir. Thank you.
Take
Allah
care.
Hafiz.
Allah Hafiz.